Hello and welcome to our video for today. We're going to be looking at using random methods to draw conclusions. So, using the idea of random selection. Sometimes there is no way to measure the total number of something. For example, how would you measure the total number of blue whales in the ocean? Even though it's not possible, we want to know the total, especially for animals that are in danger of becoming extinct. So we would want to know if there were only 2,000 blue whales left in the ocean, so that we could try to help them survive and increase. Random methods can help us do this. I'm going to show you how this is done, but as I do, I want you to use your critical thinking that we talked about in the earlier video about random sampling, because I'm going to ask you what you think about this method. Okay, here's the story. Suppose we are worried that there are only a few wild elephants left in the jungles of Kotelé. How can we find out how many? So if we catch some wild elephants, let's say 20, and we mark them in some way, maybe we put a mark on them with permanent paint, or maybe we tie something around their legs that they can't remove. And then we release them back into the jungle where we found them. Then maybe 6 months later, we find 150 elephants all together at a waterhole in the dry season. Out of the 150 that we find, there are 10 that have the mark that we put on them. Now we know that we marked 20 elephants. 10 of them, or 50%, are in the group of 150 at the waterhole. So we can say that this number, 10 or 50%, is a random number. We had no control over how many marked elephants would be at the waterhole. The last step is to say, if 50% of our marked elephants appear in the sample of 150, then the number would have to be 300 elephants for them all to appear. So the total elephant population must be 300. For me, at least, there are some fairly big questions about this method of estimating the population. Maybe the 20 that we caught at the beginning were not a random sample. Maybe we caught them because they were old and slow. Maybe there were a high number of males who are more likely to be solitary and move around compared with females who stay with the herd. Maybe some of the ones we marked and released are no longer alive. So when we measure how many did not appear at the waterhole, we get the wrong number. We are making a huge assumption when we say, because we don't control the number of marked elephants that appear at the waterhole, they are randomly scattered through the elephant population. There could be any number of reasons why that isn't true. For example, maybe the waterhole is close to where you released them. Maybe there were elephant family groups among the ones you marked, so they stick together. What if part of the population was in a place the marked elephants couldn't get to, maybe on an island? That population wouldn't be included in the estimates. What if the species is territorial and doesn't move around? The marked ones would stay where they were released, and sightings in other places wouldn't include any marked animals. In the earlier video about random sampling, we said that a key test is whether you would get the same result if you did the same thing twice. So if 3 months later you found another group of 75 elephants, how many would you expect to be marked? If the theory is correct, you would find 5 marked elephants out of 75. So here's the mass. There were 10 out of 150 at the waterhole. "75 that we found this time is half of 150. So the number of marked elephants should also be half. So half of 10 is 5. So do you think that the second group would prove that the method is correct or not? This is a made-up example, so there's no clear answer to this question. We can probably say that because of the problems we have discussed with this method, the margin of error is high. So we wouldn't expect the number to be very close to 5. Here's an activity you can try at home to test this. Write the names of 100 students on equal-sized pieces of paper. Put them all in a container and pick 20 names at random. Mark the 20 chosen names by, say, drawing a line on the paper. Put the names back into the container so there are 100 names in the container again. Now, draw 25 names. Count how many of the 25 names drawn have the line on the paper, and then calculate how many the total should be if this method works. Okay, I'm going to move right on. Obviously, you're going to have to take time out to do this. What are we doing? In the real world, we would start at step 2. So, for example, we find a group of 20 elephants, and we mark them all. We have set up an artificial situation where we know that it is 20 out of 100. But in the real world, we don't know the total population of elephants. We don't know the 100 figure. Firstly, when we found the new group, we found 5 out of that original group of 20 marked ones. So that was 25%. The logic is that if we found 25% of the marked ones, the size of the group we found them in, which was 25, must be 25% of the total population. So 25 over 25 times 100 equals 100. So they're saying the total population is 100. So if the system works, there should be 5 marked ones in our group of 25. If it's not 5, it shows that this method doesn't work very well. So far, so good. What if the number of papers with a line marked in the new group was 6? So we found 6 out of 20, which is 30%. So the calculation is 25, the size of the group, times 100 over 30, which would give us an answer of 83, which is wrong because we know the population is not 83, it's 100. If we found 4 equals 20% of 20. So the calculation would be 25 over 20 times 100. And the answer is 125, which is also the wrong number for the population. Should be a 100. If you want, you can repeat the second draw several times if you want to make a better test whether your conclusion is correct. As another variation, you could not put all the 100 names in the hat for the second draw. Leave a handful out. Don't count how many you've left out. So the idea is that you don't know how many names are in the hat. And this is the situation when researchers are using this method to estimate wild animal populations. Then you do the second draw and the calculation, and the answer to the calculation should be the number of names in the hat. So count the number in the hat to see if it's correct or close. So, question, why do we use this method if it's not very good? And the short answer is that we don't have a better method. Also, it doesn't matter most of the time if there's a high margin of error. Many people would say it's an estimate of the population, not a calculation. What we're saying is that it's good to know the population of blue whales is 2,000. the margin of error is 25%, which means it could be somewhere between 1,500 and 2,500. That's a big difference. But it's better than having no idea about the population at all. So you have to use your critical thinking. We can say there are a lot of problems with using this method, and we should check out how the population number has been calculated before we use the data in any way. There are some other ways to calculate wildlife population data, but they also have problems. It's important when we start to use the data that we don't forget that it's not very accurate. Decisions made based on data cannot be more accurate than the accuracy of the data they are based on. Think about that. What we are saying is if there's a 5% chance that the data we are using is not correct, there will be at least a 5% chance that the decision we will make will also not be correct. And if we forget this, we can make a lot of bad decisions. So how to calculate the number? Here's a few examples. A famous television channel put tags on 58 alligators and then released them. Later, they caught 260 alligators. Among those alligators, 50 were tagged. So calculate the best estimate for the alligator population. So I'm going to go straight ahead and do the answer. Up to you whether you stop to work it out or you just follow my answer. Here we go. So step 1, we make a fraction of the number they tagged at the beginning, which was 58 on the top, and the number of tagged alligators they caught later, which was 50 on the bottom. If you want to be sure you've made this fraction right, the top number will always be bigger than the bottom number. Then we multiply by the number of alligators they caught later, which was 260. So we do 58 over 50 multiplied by 260. And then we can cross out zeros on the top and the bottom of that. We get it down to 58 times 26 over 5. 58 times 26 comes to 1508. And then we divide that by 5, and the answer is 302. So the total alligator population is 302. Another example. A computer tracking chip company wants to test their chips. They marked 32 birds by attaching a computer chip to their legs. Later, they catch 440 birds. 28 of them are marked with computer chips. Then they provided this data to animal welfare authorities to estimate the bird population. To the nearest whole number, what is the best estimate of the bird population? So I'm going to go straight ahead with the answer. So step 1, we make a fraction of the number of marked birds they find divided by the number they originally marked. Big number on the top. So 32 on the top is the number they originally marked, 28 on the bottom. Step 2, we multiply that by the number they caught. So 32 over 28 times 440. And the answer to that one is 503, which is the total bird population. Okay, your turn. Noyetu has to complete a research project on the ape population in Spain. She is trying to estimate the size and population of apes. She randomly catches 37 apes and marks them with paint, and she releases the apes into the jungle. The following year, she watches 250 apes, and she found that 10 were marked with the paint that she used. What is the total ape population? So you should stop and try to do this one, so pause the video because I'm going to go ahead with the answer. So we have 37, the big figure on top, 10, the small figure on the bottom, and we multiply by the size of the group, which is 250. So then we can cross out a 0 on the top and the bottom, and we get 37 times 25 over 1. Multiply 37 times 25, and you get 925. That is the total ape population. Okay, this is about interpreting data that has been collected randomly. Here's the situation. The principal wanted to open a cafe at school. He collected data from 2 random samples of 100 students about what they like to eat for lunch. So here's the results of that. We have group 1 and group 2 in the left-hand column, and then the things that they chose out of 100 in the other columns for mama noodles, rice and curry, and noodle salad. So look at this data and try and draw 2 conclusions based on the data. Don't get too complicated about this. There's some fairly easy conclusions to be drawn from looking at it. So have a think about it, pause the video. I'm going to go ahead with the answers. So, firstly, the favorite food was mama noodles. Secondly, the least popular was noodle salad. And 3, mama noodles were more popular than rice and curry plus noodle salad added together. You could have some slightly different conclusions, but for me, those were the obvious ones. So here is the same data again. I want you to notice something here. The results from 2 randomly selected groups out of the same number of students show different pictures. All those conclusions we just looked at would be true for both groups. But imagine that instead of one researcher doing 2 surveys, we had the 2 surveys done by different researchers. So nobody is bringing the 2 sets of data together to look at the same time. The second researcher might conclude that the number who wanted mama noodles was more than 3 times the number who wanted the other options. So he had 78 for mama noodles and only 22 for the other 2 put together. So he could conclude mama noodles 3 times bigger than the other ones. The first researcher could not arrive at that same conclusion. His results show that mama noodles are not even 2 times the number that wanted the other options. So his number is 56 compared with 44 for the other 2 options. As we said in the earlier video, if you do the survey twice and get significantly different results, you can't trust the results. Here's another example. The company wanted to test a new flavor for potato chips. They collected data from a random sample of 100 people who bought potato chips at 7-Eleven. So look at the data and make at least 2 conclusions based on the results. So take your time, pause the video. I'm going to go ahead. So here's the data, same data again. Most people didn't like the new flavor. So 60 out of 100 didn't like the new flavor. Secondly, most of the ones that liked it would not choose it ahead of their present favorite. So 35 out of 100 liked the flavor, but they said, no, I'm going to stick with my existing favorite. And thirdly, the number who would change, 5 out of 100, is very small. And this is the end, my friend. See you next time.